So good afternoon. Welcome to this is a workshop session. So I thought initially it was like a classroom session, but apparently not. So I'm glad that you're all here. So I'm Ganapathy. I'm a faculty here, associate professor in the Department of Engineering Design, and I mostly work in the area of medical image analysis. And in the recent past, there is a lot of applications of ML and AI based techniques to this field. So I'm going to talk a little bit about that today. Okay, I'll be mostly be seated primarily for the benefit of the camera. It's not that I want to sit down. Okay, they've asked me to sit down so that I appear in the frame at all times, and when they put that video up, I show that. Okay, but if I do need it, I will use the phone. I don't think I will, but anyway. All right. So before we begin, just want to know how many. You can just raise your hands. Okay, it's not like you have to say anything. How many of you are in an engineering program, engineering degree program? Okay. How many are working? Okay. But you have you're all engineers, right? If you're on engineering program, okay. How many of you are in computer science? It's very sparse. Electronics, electrical, communications engineering. Okay. I just wanted to understand the diversity of the class. So not as many computer science professionals as I thought. Right? Surprising. Okay. But I don't know computer science engineering students who take up this BSc degree course. But there's actually one student in my lab who is a project associate. Okay. So it's not surprising. Great. So I wanted to know because it's going to be a very introductory level class. Okay. So I was told that most of you, not even a class, it's more like a talk. Okay. So you are welcome to intervene at any time. Some of this stuff might be known to you. It's fine. I'm going to make slightly different points than what I usually do in a talk. Okay. So this might be. So I was told that you are all done statistics courses, right? I'm only talking about your BSc program. As part of your computer science program, you might have done most of the stuff I'm going to talk about. Okay. Right. So you have done statistics, but you have not actually taken any machine learning course or deep learning course as part of the BSc program. Correct? Okay, that's I'm happy. So I have only tailored it for that. So I am assuming none of you know anything about machine learning. Some of it it's true. You might do a lot of these courses and still know nothing. That's okay. Once you apply it, you will know something. All right. So let's start. Basically, I'm going to talk about a little bit about medical imaging. Okay, so that you have to know the context. So I am an applied application scientist or an applied area scientist. Okay, so I don't work on algorithms per se. It's more adaptation. Maybe some algorithms might emerge based on the problems I'm working on. So, but medical image analysis is a very popular field. At least in India, everybody wants to work on it. The data is lot of data is freely available, surprisingly, but very few compared to what is available for computer vision. Okay, how many of you are familiar with the term computer vision? Computer vision, okay. Computer vision, okay. Computer vision algorithms, etc. You might have heard. So this is not exactly that, right? Medical image analysis works with images, but some of the methods that you would attribute to computer vision might not be applicable here. Okay. So I'm going to only talk about a certain application in medical imaging. Okay. So that is primarily called medical image segmentation. That's what we will see mostly. I'll tell you what it is because I'm going to talk about medical image analysis. Okay. All right. So we are going to be doing these three topics today. So I'll give you an introduction, an idea of where in medical imaging you have some need for automation or processing, and we'll look at how we can use binary decision trees and random forests for image segmentation. Okay, I will not give a very deep explanation of binary decision trees. It's a fairly simple algorithm. That's why I chose it. Okay, it's easier to talk about. Okay, and lot of implementations are freely available. I'm just going to show you how it's done in a medical imaging setting. You can of course extrapolate it to other application areas. Okay, and you see appreciate how is it different. This is the stepping stone to what you typically call AI or deep learning. Deep learning also comes under machine learning, but the next step would be deep learning. Okay, so this will be an easier thing to digest, especially since it's a informal setting, I would like to think. So you should all silence your cell phones or all notifications, because there are enough of you for the phones to keep ringing in frequent intervals. Okay. All right. If you want to use the restroom, go drink some water, take an urgent phone call, you can step out and do it. You don't have to ask me or anything. Okay, it's fine. Don't come in the way of the camera, try to go around it, but otherwise it's fine. Okay. All right, so we'll look at, medical imaging, right? So so when you mean by medical imaging, I think most of you would have done this chest x-ray at some point, even if you are not an adventurous kid, at some point you would have fallen down, tripped and fallen and broke some hand or something. Gone to see, that's one aspect of medical. That's the most common scan. It's called an x-ray, radiography. Okay. So the idea behind this whole medical imaging thing is to see inside the human body. Okay. So of course the easiest way to see inside the human body is cut it open, because you have to still live through it. So little bad idea. So we want to live through it also. So non-invasively, how can you look inside the body without having to cut it open? Especially not since if you're healthy, maybe just a suspicion you might have some disease you want to investigate. So typically you're all familiar with physiological measurements. Okay, physiological measurements in the sense heart rate monitoring, ECG, okay, blood pressure monitoring, your brain waves monitoring, whatever, EKG, whatever you want to call it. All those signals are there. Okay, those are some indirect ways of measuring your health. The slightly direct ways of measuring your health, especially from an imaging point of view, CAT scan. All of you would have done in a CAT scan. CAT scan provides you with cross sections of your body. So it's like you cut it open and then you're looking through the axis, right? If I'm lying down, that basically is slicing me here and looking along the Z axis. If my length of my body is along the Z axis. So it's like you're producing cross sections of the body. That's very useful for diagnosis. Doctors or radiologists are trained to read those scans and provide you with a diagnosis. Okay. So these are the most typical thing. CAT scans. It's an X-ray CAT scan actually. It's an X-ray CT scan is what we call CAT scan, MRI scan and ultrasound scans. Okay. So we will look at some use cases of where there is automation. There's certain tasks which need to be done on a routine basis in a clinical workflow. Okay. But I'll tell you a little bit more about it later. Let's just go through those things. Okay. So again, these are many of the slides. You will see that they change format, because these are I borrowed from multiple talks by my students. All of these slides except for the ones that look really bad were made by my students. Okay, so they are all talks from my PhD students, etc. So I have just used some pieces of it to give you context. Okay, all right. So don't worry about whether it's MRI or CT or anything. Okay, so whenever you are being imaged in a scanner, right, you will usually produce a volume of image. What I mean by volume is like a 3D block. Okay, so you will be imaged along this section, mostly this section. So you can image a thin section of my body here. Imagine a plane cutting through it, slicing me. That plane, if you straighten up, that's a picture. So you can make multiple such pictures like that. So this is called an axial scan. Okay, if you slice the body this way, it's an axial scan. If you slice the body this way, it's called a sagittal scan, sagittal view, and one more plane is along this direction, right? If you face down like this, that's called a coronal scan. So mostly when you do a medical imaging study, at least nowadays, you will end up with a bunch of these scans, that is slices as they are called, and you can stack these slices. When I say stack them, not physically, like an array, like a 3D array. I'm assuming some knowledge of array, etc. So that let me know if you don't know what that means. So like an array, and it's a 3D array. So you can index that image by its pixels, and each pixel will have 3 indices, I, J and K. That is the 3-dimensional array, right? So if you the Z will vary. When you vary Z the index, it will vary like this. It will go from one selection to the other in the human body. Okay, that's typically how you would acquire images in the human body, right? So in this case, we are looking at the heart. Okay, I think I can do it here, but I'm not sure whether this will work very well. Okay. So this is the heart. Okay, this piece here is left ventricle, right? This is the most important thing for your body, because this is the point from which the blood is pumped out into the body. So when you say heart beats, it's a left ventricle is getting squeezed, spin and squeeze, and that's where the blood is pumped out. Okay. So when you are acquiring images of the heart, this is using MRI. Okay, let's not worry about imaging modalities or systems. We just see what the pictures look like. So when you image the heart, the left ventricle is the target. So typically they will acquire the so-called short axis image. That's the axial image right there. This piece, these slices. So if you cut it, you can cut like this, right, along this direction. So you can move this plane along this direction, along the length of the LV. That will give you short axial slices. That's what it's shown here, short axis planes. You can also slice the resultant volume with this plane. You can move left or right if you want to think of it that way. That's called the long axis plane. That's what I call the sagittal plane. Okay. The other one is the 4-chamber plane, where you cut top to bottom. This is with respect to how you are oriented, right? You will be lying down in a scanner. That's your orientation of the heart. Okay. So these 3 planes. So once you have those 3, what do you do with it, right? That's the question. Okay. So I have just so this is for especially for cardiac imaging, right? This is there are 2 aspects. One is you are imaging the entire heart volume, different sections at every time point. So your heart's beating, right? When you say heart's beating, a very easy way of thinking about it is heart is filled with blood, and it's bigger. The chambers are bigger because one chamber, especially the left ventricular chamber, is bigger, and when it pumps it out, it becomes smaller. Okay, so that entire action for you, that typically would happen in a second, from filled to pump out. Okay, so that people typically in a diagnostic setting, they would want to image that. Right, so that's what we are looking at. So if you look from diastole is when your heart is full, all the way to systole. So this is in time. Previous one was in space. These slices are in time. Okay, so MRI allows you to image one heartbeat. Okay, so you can image your heart like still photography. Imagine like still photography, right? How they show you bullets coming out of the gun. So you can, at every point in which the heart is getting compressed, you can acquire the entire volume of the heart. Okay, so that will give you volumes over time. Okay, they will give you volumes over time, and this is just one section of the volume. So you take one plane and plot it over time. So you can acquire that. So that's the complexity of this image. This is why I chose this, because it has both the time and space complexity. So it gives you 3D picture of the heart at every time point during one heartbeat. So if you look at this very bright piece here, that's when your left ventricle is full. If you look at it here, slightly compressed, a lot of it has come out. Okay. So of course it's not exactly at, it is called systole, full systole. This is diastole. The systole is where it goes down. So sorry, I pointed at the wrong time. So you can see it's fully filled right here. Go down here, there it's compressed. So a lot of it has been pumped out, and then it fills back again. Okay, so that's the time you can image an heart. If everybody able to see, right? If you don't understand, let me know. I'm just trying to let you appreciate the complexity. Okay. So then once you have this, so you can actually make a movie out of this, right? So just you can see how the heart beats. Okay. So that's the kind of temporal resolution that is afforded by MRI. So there's a lot of hardware thing there, but we still have to analyze this picture, right? You can imagine. So when you are imaging the heart can be covered with about 250 sections. Each section is of size 256 by 256. This is a grid. That's like a picture grid. I'll show more later. But this is typically what you can do over time. So you're looking at a particular cross section. This is the axial plane. On the leftmost is the axial view. That's a short axis view. This is the sagittal view, and this is the coronal view. So you're looking at different cuts, but over time. That's typically what you're doing. Okay. So now we have this. Okay, what do you do with it? Okay. So we're coming to the point as what kind of problems are we trying to solve with machine learning? Okay. So why do we just to explain, this point, okay, is what appears as the line here. You understand? So if you think about it, you are just, these images here are cuts like this. Okay, that's what this shows. Okay. So we are just looking at the same beating compartment along different axes. That's all. Don't have to worry about it too much. So if you Google this or search on this on the web, there'll be a lot of explanations. But at this point right now, you can see that at a particular section of the heart, you can see the blood being pumped in and pumped out. The blood appears bright in these pictures. Okay, and make it that way. All right. So, what is it that we want to do? Okay, from the point of view of diagnosis, right? What people typically want to estimate are three things. Okay, one is this left ventricular volume when it's completely filled, and when it's completely pumped. Because from the left ventricle is where it is pumped out throughout the body. Okay, so when it fills and when it's completely empty, you want to know the volume of the left ventricle, which is the blue area. Okay, the green area is called the myocardium. Myocardium is the heart muscle. So the heart is actually a muscle. Okay, so the muscle is what pumps it out. Okay, think of it like a twist. You have a bag which is surrounded by muscle, and it just squeezes that bag and pumps it out. Okay, so the heart muscle and the right ventricle is, these are very simplistic notions. So I am not a doctor. Okay, so just for the sake of argument. So there is heart motion pumping is much more complex than that, of course, right? Just a disclaimer. Okay, in case you do something based on what I said, right? Don't want to be in trouble, right? So right ventricle is again this one of the other compartments from which the left ventricle is filled. So these three volumes, the outlines of these compartments is what is sought after this imaging session. Okay, so typically a radiologist would draw, or there will be some technician who knows anatomy who will draw by hand. Okay, so once again, just before we go any further, see, CMRI, especially in India, is not done much. Okay, it's an expensive thing to have. MR systems by themselves are expensive, and not all MR systems can do this. This is called CMRI because you are trying to capture the entire volume of the heart in one heartbeat. Right? It's less than a second. You are getting tens of 30 to 50 volumes to show the heartbeat. So it's an expensive protocol to have installed on your MR machine. So it's an expensive machine to have, but still it's a very useful diagnostic tool, and people turn to it all the time. So in that, given the context, you know the context, right? Not everything you do with medical images can be useful. Okay. So this might possibly be a useful thing to do. A lot of people should be pursuing it. Okay. So you should also go talk to a radiologist, see whether he will use such a thing. Okay. So anyway, I will talk about that later. So generally, so this is the task. So this task is called segmentation. And remember this, I have shown you this in one slide. You have to do this for the entire volume of the heart. So I will show what that means in the later slides. Okay. So how many of you are familiar with the term semantic segmentation? Segmentation? Pixel segment? No? You haven't heard segmentation? You heard of? Okay. So segmentation or semantic segmentation in computer vision is when you are given a picture, right? You take a photograph with your camera, or for instance a movie video with your camera. You want to label every pixel in those images as belonging to a particular category. So for instance, mark all the humans in the picture, mark all the cars. When you say mark all the cars, it's just not drawing a box around it, but also indicating what are the pixels that belong to the car and what do not belong to it. So that's the idea behind segmentation. It will end up looking like this. So here, all the pixels corresponding to the myocardium, which is the muscle of the heart, is given a certain color. When you say color, you just give it a label. Okay, label 1, label 2, label 3, so on and so forth. So each of them have different labels. Okay. So we will come back to this. So what I am going to show you, this is when I come back to this, the method itself. See, there are two steps here. One is you have to identify, do this segmentation, which is what is shown here. Raw image to segmentation. Here it's not shown in color, but in different shades of grey. And following this segmentation, you have to do this piece, which is called disease prediction, right? But there's a point to all this, right? Why do you want to do all that? Well, all you want to do in the end, what would be ideal is the entire system predicts after the scan, does the analysis and predicts that whether you have a disease or not. Okay, so that's why it's in two stages. One is the medical image analysis part, the other one is the disease prediction part. Okay, so mostly this is where a lot of the machine learning techniques are still applied. Okay, so this piece in many cases is still not deep learning, wherein you extract quote unquote features following your deep learning algorithm, which produces this labeling. and then use those features to do disease prediction. I'll show you some what that means. Okay, so this is just a use case. There are other use cases also. Okay. I'm going to show you a very simple algorithm. Don't worry. It's not meant to bore you 2 hours with something that you will not be find entertaining. Okay, just to understand, because I come from the applied medical imaging side, I like to proceed this way. Okay, it's up to you how you want to do this. Okay, so this is the methodology, but again we'll come back to it. So this the first step of this pipeline where you see this the white boxes, right? The white boxes where this is where so-called deep learning happens. Okay, the deep convolutional neural networks or artificial neural networks, they will produce this pixel-wise labeling. All right, and following that labeling, the green boxes is where the other kind of machine learning algorithms are used. You can still use neural networks there also. I'm going to show you a slightly different algorithm. Okay. Okay, so this is again, we will come back to this, but it's not very important. This I'm just trying to show you the kind of diseases that can be diagnosed with this kind of analysis. Okay, there are lots of diseases of the heart. I don't know most of them. You must have heard of some of them, right? Heart attack is one. Okay, and heart attack happens for a variety of reasons. Okay, one of them is when you have this so-called myocardial infarction. The muscles in your heart die because there is no blood supply, and it stops pumping, leading to a fatal event. Okay, that's one of the diseases that you can diagnose with this kind of analysis. Okay, there are these abnormal right ventricles, very thick myocardium, and there are other different diseases that I have mentioned here, right? So we will not go into details. This cardiomyopathy is DCM, hypertrophic cardiomyopathy is another HCM. So there are different types of diseases. Each of them has its own kind of symptoms. So for instance, if you look at this particular case, you have a small left ventricle. Okay, the left ventricle, like I said, is where the blood is pumped out from into the body. So that's, of course, you can see with our analysis, you can find out the volume, and based on that you can judge. Okay, so this is one. These are the few diseases that can be diagnosed. Okay. Okay, let's just go. Finding it hard to move through slices. I just want to show you what I mean by volumes over time. Okay, so this image just shows you the complexity of this task. So what you see is I am scrolling through the heart, the levels of the heart. Okay, right from the base of the heart to the apex, top to the bottom. Okay, and this is one volume at one time point during your so-called cardiac cycle, which is basically one pump action, right? So the heart fills with blood, pumps it out, and during the time period you are carrying entire volumes of the heart, and this is just scrolling through that volume, scrolling through different sizes of the heart. Okay. So if you want to understand this slightly better, so here of course you can see that the prediction is pretty good, but I want you to understand the where these images are so that you know what I am talking about. So for instance, what you see on the top left, it's a 3D rendering of the heart. So if you take all the images, okay, and let's say you threshold out the heart in every picture, put them together like a solid block, that's what it will look like. So those images that you see are nothing but slices through that block. Okay, so what I showed you now, that movie, was basically me going through the height, slicing at every plane. So this plane extends into the plane of the screen, right, this way, and so each slice will give you a picture. That's what we were looking at. So this way, right? So this is how I explained to you the process of one of the use cases in medical imaging where it's used. That is basically you want to do so-called semantic segmentation. That's one way to do it. Okay. So now this convolutional neural networks, so-called CNNs, dominate this kind of tasks. Okay, all the best results in the field of semantic segmentation, starting from computer vision all the way to medical imaging, best results come from convolutional neural networks. Okay, you must have heard them. If you haven't, since there are too many blank stares, CNN, you must have seen convolutional neural networks. Okay. But right now I am going to only talk about binary decision trees. We will talk about it later, don't worry, towards the end When you really want to leave, we'll talk about it. So then, all right. So I'm not going to go through the results now. Once again, each of them show the results at different phases of the heart for different disease conditions, etc. Okay. Let me go back to once again. Just want to make a point here. If you see here, I don't know whether you're able to appreciate this, but let me see this little. What happened? Right here. So you see, it's not very visible here, right? The input image. You see that the very small. The compartment has become very small. So basically, you're at the piece where you don't have too much blood in it. Okay. So this is where all the errors happen. Okay. Just appreciate this point, because lot of times in most of the, if you take any algorithm, right, most algorithms will do comparably in most places. Only in the very edge cases you will get performance improvements. Especially this particular task, lot of algorithms do comparably well. Okay, so and even among CNNs, there will be like 10 different CNNs, they will be off by 0.5 or something percentage. Okay, it's really small. Okay, and we don't know whether those things make an impact on the diagnosis. Okay. So any questions? So I'm going to give you guys a small break so that it's too much to. If you don't understand this, let me know. Are you able to understand the anatomy a little bit? So where we are taking the pictures? Yes. If you don't know, please let me know. Okay. That's just slices. Yes. 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 Why it slices? Because that's how the images are acquired. That's the signal that comes to us. Okay, he's asking why do you have to slice it? Why not some big 3D chunk? Yes, we can do that too. But even then, the way MR imaging works typically is you have to acquire one section at a time. There are sequences which do the whole thing, but typically it's only one section at a time. CT also, it's only one section at a time. That's how it's acquired. Okay. So it's not a construct we put in. That's how the image comes to us. Okay.
60 frames maybe in a minute? Or
so this need not be real time. This can be done offline.
but sir, how if that give us like extra information over like time information that we are missing in that?
Okay. So here I have only shown you one volume. So this is just answering his question. So hold on. This is one volume. I'm slicing through one volume. So you will have to do that for. So you don't have to do it for all the volumes you acquire during one cycle. Yeah. So the idea is you will extract the volumes from once you segment the left ventricle over time. You know its smallest volume and you know its largest volume. They calculate a quantity called ejection fraction, which is an indicator of how good your heart is working. What is the difference between it's something that is proportional to the difference between the largest and smallest volumes of your left ventricle. So the idea is, again, there are some diseases where the myocardium, the green piece, is thin. So that part also you need to calculate volumes or thicknesses. That's where it helps. So the segmentation by itself, just by looking at it, it's no use. There is a quantitative markers which are taken. I'll show you some of them right now, then we can see. Any other questions? Okay, I'll proceed. Just keep track of the time a bit. I just realized that if I talk this way, I think the mic picks up better than if I'm facing this side. That's okay, I mean, it doesn't matter. I have a loud voice, I think most people can hear me without a mic, several buildings away. So, yes, so we will we'll go. Okay, so he was asking me, right, his question was very useful. Yeah. So why do we do this? Right, why do we do this in the sense that you saw this fly through, as they call it. We can see with the naked eye. Most radiologists manage to see that with the naked eye. So what's the point in doing that, right? So whatever we can perceive, anyway, see, now the clinical setting, radiologist has to go, doctor has to go look at it. So it doesn't matter whether you do this or not. So what is it that we can, how does it help? It helps you extract some information automatically. Okay. So, and these are some of the features, quote unquote, that can be extracted from the segmentation. So for instance, volume at ED. What is ED? ED is end diastole, which is you can think of it as when your heart stops filling, right? Your heart, that means that your left ventricle is being filled with blood and it reaches its maximum value, and you know its volume. Okay, that's one metric. How do you do that? How do you calculate that? How do you do that with the segmentation? So I'll show you again. This, see this blue is the volume. This is the blood volume. So how would you calculate the volume? Knowing this segmentation map. Yes. So you know where the blue pixels are. You can do thresholding. Correct. You find out. So blue pixels means it's just a label. It's just a fake image with a label. So you find out where all these labels are. Let's say blue is label 2. Find out all the pixels with label 2. Count them. And you count them for every section. That's the volume. Okay. So one thing about medical images is that the pixels actually have dimensions. Okay. So each pixel has a dimension. It's called a voxel. So it represents the volume of tissue. So you have dimensions. So so these are many of the where was I? Okay, I think I went too far past it. Oh yeah. These are some of the many of the calculations that you do post segmentation. Okay. So now once you have these numbers, this forms what is called your, so this piece here. This is your feature vector. Okay. So for every patient, it's how many points are. So it is some n-dimensional vector where n is what the number of features here. So each one of these quantities that you get out of the image is a feature. Thank you. So that is, you can use this in a lot of machine learning algorithms. So one algorithm that I will talk about is binary decision tree, which is, I don't know why this is actually not working very well. Sorry about that. So we'll see binary decision trees. Okay. So there are multiple applications here. So once you have this list of, acquire this list of features, and you have the ground truth. The ground truth is basically where for this particular patient, you are given whether that patient has a disease or what kind of disease he has. So that's the label. The disease is the label. So what is the label? So let me go back. I showed you that sometime. Right? Sometime I miss this. Yeah. So let's say this is label. This is a normal heart is label 0. This one has a disease called DCM label 1, label 2. This is label 3 and label 4. So for every heart that you are imaging, you have this ground truth data where after segmentation, you obtain that vector from the segmentation and you have the labels corresponding to these diseases. So you are going, this is your Y. So this is your YI and that's your X corresponding to this YI. Okay. So now you have that X and Y, all you have to do is train a machine learning algorithm to predict these Y's from their X's. So the X's, once again, just to show you, it's your X's. Each of them is your X. So if you want to treat them like a vector, so for a patient, I'll denote a patient by in the superscript or subscript, I don't know which is better. So the patient index is the superscript, your feature index is the subscript. Okay. So x1 would be your volume at ED, this would be x1, x2, x3, so on and so forth. So for any patient that will be there. Okay. So this is your feature vector. Okay. So I walked you through this because for, if you didn't have, I hope that most of you would have been exposed to this. If not, you will study it in later sections. If you did not have, let's say, your convolutional neural networks, your deep learning algorithms, this is what you would be doing. You will figure out some way to extract these features. Okay, and from these features, you would make a hypothesis, which is basically what disease can I predict with these features. All right. So that's and one of the algorithms that lets you do that is your binary decision tree. Okay. Is that a problem? All right. So we will come back to this at a later point. Okay. This is just the binary decision tree as an algorithm lets you know what feature contributed to the decision the most. Okay. So this plot that you look here is called interpretability. I call this interpretability. Let's say an unlikely event that some doctor actually uses this program, okay, and says, okay, you have some disease X, okay, one of those 5 I showed you. Then you ask why, right? So then he can actually, the algorithm does allow, at least the binary decision tree, does allow to go and look at what was the most important feature in that particular diagnosis. Okay, so that's why I call this interpretability. So what binary decision trees allow is that since you list the features, okay, you can actually figure out which feature contributed to a particular decision most. That's something that you can do with the binary decision tree. Okay? Some other algorithms allow it, but that's the most easiest thing. Okay, so just remember that. So that's why I showed you this. So it's called feature importance. Yes.
This bypass feature importance mean that there are 5 significant components into the.
No. Sorry. Good question. Sorry. I'm sorry to cut you short. No. This is a 5-class problem. This is a 2-class problem. So I didn't. So why the 2-class problem appears, I have not shown you. Please ignore this side of the picture. Only concentrate on the left. I showed you 5 disease conditions, right? Yes, and that if you don't remember that, good. Somebody should keep asking me questions because I know everybody will go to sleep otherwise. So here we see 5 disease conditions, right? Normal, okay, and one is called DCM, dilated cardiomyopathy. That's here. Sorry. This is called hypercardiomyopathy. I think hypertrophic cardiomyopathy. That's right there. This one. This is the enlarged left ventricle. That's another condition. And this is the infarcted heart. So 0, 1, 2, 3, 4. 5 conditions. So that's 5 classes. That clear? Or you have more questions?
So it means 5 possible
Outcomes. Yes, 5. The 2 class comes because I will explain that later. It's not important. It is some tweak. Some tweak we did, because what happened was whenever we predicted a certain disease, it could be either one of 2. Let's say we predicted 4, it could be either 1 or 4, like that. So in order to break that tie, we made one more, and that's the 2 class. Okay, so don't worry about that. Okay, that's we will go there. Yes, this is a good question. Okay, so this is the feature importance. So forget the one on the right. The left is the 5-class problem. 5 diseases. We have a lot of these features. With these 5 features, we are getting 5 outcomes. Okay, we can do it with lot of algorithms. One of the algorithms you'll see is a binary decision tree. Okay, so I think I mentioned this also somewhere in the earlier slide, but anyway, that's one of. Okay, so we will not look at all this. This is called the confusion map. Let's not worry about that right now. We'll come back to it when we have the time. Okay. Okay, so that was one exciting problem. Okay, so any more questions regarding that? So I haven't told you that algorithm yet because it's a very simple algorithm. That's why I'm not telling you so. Yes. Okay, I'll have to think about this. Sorry. So this might be because they might be redundant, is what I feel. So if you remove them, they might not make a big difference to your outcome. So one of the things with doing this feature extraction by hand is that you will have to do a lot of them and then throw them away little one at a time, because many of them might not have any impact on your results. Okay. So this is what most people were doing, finding out what is more important in a part to automatically classify into a disease. Okay, so I suspect that these are either redundant or in this case I would just stick with that. Okay, I don't want to guess too much, but yes, but don't worry about that. Just only behind the plot is basically that there is a way to figure out what contributed to your outcome the most. Okay, so the end systole volume seems to play a huge role. Then EF, the second one from the top, if you can read it, it's the ejection fraction. Ejection fraction is your maximum volume of the left ventricle minus the minimum volume of the left ventricle, so that you have pumped out most of the blood that's in the heart. Your heart's working well. Okay, that's the thing. All right. So Any other questions if you want to? Oh, have you guys ever looked at a confusion map before? This is not the confusion you are experiencing now, but confusion map here. Okay, that's very useful in any classification. Okay, so I might get this wrong a bit, but you can always go back and switch this around. So you have this, you see this matrix here, right? This is a confusion matrix. Okay, so if you look, ideal confusion matrix should be diagonally dominant. In the sense, all the diagonal elements should be very high compared to the off diagonal elements. It's usually a square matrix. So if you have 5 classes, or if you have 10 classes or n classes, the confusion matrix is n cross n. Okay, and what does it mean? It means that, let's say you are testing your algorithm or even training. After training, you run through all your samples through your algorithm, and it spits out, for every sample it split out a class. Okay, so what this confusion map shows is, if I have, for say, normal heart, okay, I have 10 normal hearts, 10 patients with normal hearts. Okay, all of us have normal hearts, talking about a physical heart. Okay. So 10 patients who don't have any disease, and 10 out of 10 times I got it right. Okay, it is, if your x is the real thing and your y here is what you predicted. Okay, so 10 out of 10. So DCM is a disease condition. I had 10 patients who had DCM, but 8 times I said it's DCM correctly. Twice I got it wrong. I misclassified as MINF. Okay. HCM is another disease. So out of 10 patients, I got it right all the time. Okay. MINF, myocardial infarction. 10 patients, 2 I misclassified at DCM, 8 I got right. Okay. RV, right ventricle being enlarged, 10 out of times I got it right. This is actually a very, very good matrix. Okay. Usually you won't get it like this. Okay. So this will be, more it spreads out, the worse it is. It should be diagonally dominant. So confusion matrix you always do, because it helps you classify true positives. I will not explain this now, but you can always go back and look this up. True positives, false positives, 2 other quantities. This is homework for you. Please look this up, very important. Sensitivity and specificity. Okay. So you must have seen, you all done statistics. How come you don't know? No? Confusion matrix, yeah. This was taught in your courses, right? In your basic course, or at some point you have read yourself, that's okay.
Not in the stats subject.
Okay, fine. At some point it was taught, right? You don't know? Okay, who's, she might know, Nikita might know. Okay, anyway, she said she was an instructor for this. It doesn't matter anyway. If you don't know, look this up. Okay, I'm not going to it, but this is an idea behind it. So you make this big matrix and see what the misclassification is. Ideally, diagonal should be very high, off diagonal should be lower. Okay, gives you an idea, and you can calculate these quantities from the matrix. Gives you an idea of how well your algorithm is performing. Okay, so this is okay. Not too bad. I don't have to actually go 2 hours. Okay, I can finish earlier. Just don't want to you to feel cheated, right? Okay, so before we go into all this, right? So I was just making some flippant remarks about the unlikely event the doctor uses it and all that. The problem is, okay, so a lot of times, many of these methods that are now, these are all published. These are papers that I have, you can look up my publication, there are many publications like this, okay. So the idea is, you know, all these fall under what you would call computer aided diagnosis, okay. So now, how many clinicians, how many doctors, etc., will actually use this every day? Okay, most people won't. There are some areas where it's absolutely necessary, right? At least, see, for instance, there are scenarios where it's necessary. So, for instance, there are these times when they do something called screening. Okay, screening is when you scan a very large portion of the population for a certain disease. So, for instance, breast cancer. Okay, a lot of women are at risk of breast cancer beyond a certain age. I say a lot of women, a significant percentage of them, right? So given our population, even 5% is a lot of people. Right? So when you have such large studies, okay, and then there's a large hospital, lot of people come in, let's say it specializes in a certain disease. Lot of people walk in with heart disease. You're scanning them every day. Then some of this automated analysis can be helpful. Okay, that's a first step. You would eventually all of this eventually has to be certified by an expert cardiologist or radiologist before any decision is taken. But this is the first step. Maybe you can flag, this looks bad, and somebody can take a look at it. Okay, at this point that's the best scenario. Okay, of course there are some of the ML or machine learning based products have obtained so-called FDA approval. In the United States, they have this body that approves these things, and people generally seek that because otherwise insurance won't pay. That's one thing. Okay, so it's a much complicated subject. But then even at a very practical level, many of these techniques might not be used at all. Okay. Once again, having said that, it's not useful at all. So for instance, just to let you know, if you didn't know, many of the scanners ship with the workstation. Okay, which will have many of these techniques already there for the doctors to use, and they do use them at that level. Okay, so independently, would an automatic diagnosis, a CAD system, would that work? So for instance, when I say the workstation ship with many of these methods, so for instance, those workstations might ship with the segmentation technique, where you label the pixels. That will work, but the diagnosis they might not use. Okay, so similarly, there are many things. So for instance, I have asked in the context of this brain tumor. Then I'm going to talk about brain tumor segmentation. Now, the context of brain tumor segmentation, for instance, I have asked a few clinicians, and they are very reluctant to use this. Okay, so why? Because and I'll tell you where it might be used again in the same context. So because see, for instance, in this particular problem, we're looking at brain tumors. We're trying to estimate the volume of the tumor pretty much, or the extent of the tumor. See, that can be done very quickly by hand. So what people will do is, they'll find the longest section of the tumor, the shortest section of the tumor, fit an ellipse to it, work. Okay, like an ellipsoid, that's it, you can easily find, or make it like a rectangle, whatever. So that volume is done trivially, and that's a good indicator, good enough. Okay, so this very complicated technique to segment and all might not be adopted so easily. Okay, on the other hand, some cases where you have surgery, image guided surgery. Okay, so you want to know exactly where the tumor is, exactly where a certain anatomy is when you are operating it, maybe under a microscope or under some guided, when I say image guided, then these techniques might be adopted. Okay, otherwise it's not very obvious where these will work, at least to me. Okay, and I have asked, a lot of people have the same feeling, but once again, all of these are useful in a research context. Okay, so then you might say, what do you mean research context? So for instance, somebody is trying out a new cancer drug. Okay, so they will be giving it to quite a few patients. Okay, and you want to know whether that is working. One easy marker for figuring out whether a drug works or not, especially on tumors, is you measure the volume of the tumor. Okay, accurate measurement will be helpful. Then in those scenarios, these techniques will be used. Okay, so everyday clinical practice, like some magic, we walk in and everything happens by itself, that and all will take some time. I'm sure it will get adopted over time. As of now, it's not there anymore. So for instance, this COVID epidemic prompted a lot of people to put out, let's say, automatic chest X-ray diagnosis. Okay, so it will scan. If you input is a chest X-ray, output would be a report. Many people are using that now, apparently, because many people walk in, right? So then you can't do it. You need as first opinion might be very useful. That's good. So whenever there is a need, this niche that can sit there. Okay, in general, like everything's moving towards this direction, but adoption on everyday practice, every hospital using this. There are many other constraints here. We will not go in there. We're just going to talk about methodology, but it's giving you a context. All right. So the second use case, that was a 3D plus time. This is just 3D. Okay, this is typically in brain imaging, and specifically in the context of gliomas. Okay. So let me go quickly to this part where I can show you these are the techniques. I actually had a different slide. Okay, I think I put it too far back, which is my fault. If I want to go all the way there, it's a pain because I have like 100 slides. Okay, so don't worry, I'll never go through them. Okay, all right. So so the brain tumor segmentation. This is the definition of the problem. Okay, so so this is, I like this one too. Okay, reason why brain tumor segmentation. I chose it when my lab works on this. Obviously, otherwise I won't talk about it. The reason I chose is completely different, but this is a very popular data set. Okay, it's called the BRATS data set, Brain Tumor Segmentation Challenge data set. It's freely available. It's open source. You can use it. Open access. You can use it. Okay, at any time you want to explore these things, it's readily available. So the problem is also complicated because it involves 4 volumes. So MRI is a very flexible imaging category. Okay, so the same tissue, it can provide different contrast. What I mean by contrast? So let's look at this. Look at the bottom 3 images. Okay, you see it's the same anatomy. It's a slice through your brain. Okay, you can see that this looks very bright everywhere, which may be a small dark region here. This looks very bright patches somewhere here and there. This looks completely different, but they are all the same anatomy, same scanner, but because the signal acquisition in an MRI allows you to bring out these 3 different types of contrast. Contrast is nothing but how the grayscale varies, the pixel intensities vary. Okay. So now, from this particular picture you can get the whole tumor. So this yellow kind of color, it's yellow, right? I call it yellow, whatever you want to call it. It's whole tumor. That brown, if I'm not mistaken, it's called the tumor core. Okay, and the blue is called the enhancing tumor. That's where all the blood vessels are forming. Okay, so these are 3 compartments, or in this case there are 4, right? 1, 2, 3, 4 compartments. The blue, green, blue, this brown, yellow, whatever you call it. Okay, 4 different compartments in the tumor itself. So this is the segmentation challenge. You have to label each of the pixels corresponding to each of the compartments. Okay, and doing this helps you get again this is one slice. You can imagine, like I showed for the heart, you can go to the entire slice of the tumor, volume can be obtained. Okay, so what are the challenges here? So this is one step in machine learning. You should all know this. Okay, this is an important step. First thing is obtaining ground truth. Okay, so in the context of medical imaging, how do you get ground truth? How do you know what's right? This is important. If you want to train anything, even the ones I'm going to talk about, you want to know what's the correct answer, right? So for instance, all these other computer vision tasks. How many of you heard of this ImageNet challenge? ImageNet database. Raise your hands. ImageNet. No. Okay. So it's a very popular database of pictures on the internet. Okay, so each picture will have like couple of objects, and it has been labeled as, that picture's label is that object. So it will have a cat, means the object label is cat. Like that, there are millions of those things, but it was obtained by bunch of people labeling them. Like somebody has to sit down and say what it is. Just like I had for the heart patients, we had 5 different categories. So 1000 categories, and you have to choose one of those. That's the ImageNet database. Okay. So, but here it's even more challenging. Okay, slightly more challenging, but also easy to do. Is somebody has to draw where the tumor is. So I mean, literally, I'm talking about somebody has to sit down and, did I do something bad with this? Okay. So let me do this. Take pen. Somebody has to actually do this. Has to go and, sorry. Just to do that, this is one slice. This is one section, like we saw for the heart. There will be 100 sections to the tumor. So in every section, you have to go and draw this line. there will be like 100 patients. So you can imagine how much, and you have to do this correctly. And you have to do this for every one of them, in the sense, outline of the whole tumor, outline of the core, and then go back, outline this piece, and then outline that piece separately. So you have to do that, and somebody has to do that, right? How many people do you think can even do that? Very few. Yeah, this is a huge challenge in medical imaging. Okay, not everybody can do this. You have to train them to do this. It takes a long time. So then, let's say you have done it. What then? So this is one of the places where again you can pay attention to, because in a job, when you get a job, hopefully all of you will, this is what most of you will be doing. How to figure this part out is the hard part. Okay. So once you have 5 people marking it, 5 people will mark slightly differently. You can see that I don't know whether it comes across very clean. You will see all the blue lines are basically people drawing on top of it. 5 people independently drawing. Okay. So when then 5 people have drawn and given it to you, you have to get a consensus. So there are ways of doing it. You can average it. Okay, you can average line by line and then decide, okay, this is where I will put my mark. Okay. So creating the ground truth, the important piece. Okay, you have to figure out a technique. In fact, there are companies which write software packages for ground truth markings. I don't know whether you know that. There are software packages to do that. So you can load an image, mark. It will learn as you do it and help you mark faster. Okay, that's a business. Okay. So we can do that for this also. Okay. Second, what do you know? How do you define correctness? How do you define correctness? So in this case, this is an example. The blue is the correct answer. Okay, the blue curve is the correct answer. Red curve is what my algorithm figured out. Okay, so how correct is this? What is the measure? So there are 2 things. Okay, so when you train any of the machine learning algorithms, there will be a loss function, quote unquote, something that tells you how good your answer was in the context of training the algorithm. Once you finish training and you run it through, you will get an output. There is another metric to evaluate. Okay, so that is different sometimes. Okay. So now with deep learning techniques, they can both be the same. That's a huge advantage behind deep learning. Okay, but here you have to do this. So here for mostly again for the context of medical image segmentation, the metric that you would use is called DICE. DICE is basically how much the overlap. So it's basically, if I want to write here, it's P1 intersection with P0. Here again, P1 is the entire area. So what I mean by area is like everything, all the pixels. So it's like a set, right? Like a Venn diagram. So if you overlap these two, what is the common pixel? So what are the common pixels? So you are in this case, this is misbehaving badly. Okay. So I lose this. So here, this is that small, tiny, let's say do some other color region here. That's the overlap region, the quantity of that overlap. So 100% overlap means great, smaller overlap means not so great. Okay. So this is one way, because this is your evaluation metric. So this is called DICE. Can you read this? Yeah, okay, DICE, okay. DICE coefficient. Okay. There are other ways. The other way to do it is you can measure distance between contours. What is the maximum distance between these 2 contours? You take all the point in the contour and then all the point in the red and the blue contours and find out the maximum distance between them. Okay, that's one way. There's something called Hausdorff distance, right? I think it's the minimum of the maximum distance between them. So something of that sort. Okay. So there are many ways of doing that. So that's how. So you have to figure out this metrics. Okay. So once you have this in place, lots of algorithms. Okay. So I'm going to explain one algorithm to you. But I think we are at that part where I can actually talk about. Yes. Go ahead. Finish your statement. Sorry. Yes. Correct. Yes, exactly. Okay. I probably didn't explain the context well. See, when you train these algorithms, I didn't actually walk you through how the algorithm outputs the correct answer, right? So in order for it to do that, you need to give it samples which contains the actual contours or the labeled pixels. So somebody has to do that first. So your so-called training data is basically a bunch of images where people have actually marked what is the correct answer. I'm just telling you how that is done. Typically, you would ask more than 3 to 5 raters, experienced people, to mark those regions. Like you said, the 5 regions. Yes, so that somebody has to, same thing for medical imaging. People are trained. For instance, a lot of radiographers can do X-ray and CT. MR also, so we can train people with some basic healthcare degree, health science degree somewhere. They can mark this, but you have to train them. You have to train them, and or you have to be sure that, because see, so the reason why I'm stressing this is nothing can get better than this. This is as good as it gets, no matter what algorithm you use. Okay, so that depends on how you do it by hand. So you have to show it the examples. So your output or the results of your algorithm will be only as good as the results of your markings. This is in the healthcare context. It's true for pretty much everything, not just this. If you're just doing computer vision, trying to follow cars in traffic, etc., it's all the same problem. Okay? And people have to do that. Everybody. So, for instance, if you are self-driving cars, people are trying to do self-driving cars with cameras, right? So then, for vision, you have to actually outline cars, because to prevent collision, you can't just have a box around it if you want to drive properly. You have to know exactly where the car is in front of you, etc. So then you have to know exactly where the pixels of the cars are. So then all those are done kind of semi-automatic way. Okay, so this has to be the same for here also. Somebody has to mark them. Once you have 5 or 6 people marking them, you take a consensus. So the way, one very simple example of consensus is, you take every pixel in the image and see what label each one of them has given. You do majority voting. Let's say 3 out of 5 you say it's tumor, you call it tumor, that's all. Okay, that's one way of getting consensus. There are other ways of doing it, let's not go there. Right now that's the easiest way. Okay. Alright, this is the tree, these are the important, it's just been an hour. I thought I have spoken for a long time. I'm sure you feel that way, but I don't feel. I don't know how you feel about it, but I thought I was almost done. Okay, but I'm almost done. Very soon we'll end. But I wanted to the reason why I spent so much time on this is you have to understand the problem. Okay, so again, some more pop philosophy, if you want to call it. Okay, so there are different. Since all of you have taken this BSc Programming Data Science, or it's called AI course, right? BSc Programming and AI. There are 2 streams, at least in my opinion, right? Most of you have a job, some of you have a job. You might find it useful in your job, so that's okay. That's a different thing. On the other hand, some of you might be looking for a job or might want to do higher studies. Okay, so there are 2 different ways here. Okay, so for instance, in my context, if somebody asks me what I do, I will say medical image analysis. What is my research topic? I will say medical image analysis. I will not say AI or ML. Okay, so you have to think about if you fall in that kind of category. When somebody asks you, will you say I am an aerospace engineer, I am an accountant, I am a business analyst, right? If that's what you are, then you have to understand these concepts I told you now better. Okay, how do you gather data? How do you label data? How do you define correctness? How do you remove false data? All those are wrong data. That's very important, because then you just use an existing algorithm. Of course, you have to know some programming, understand what the algorithms do, and use them in the context of your profession, specialization. That's one. Okay. So for that, you have to prepare yourself slightly differently. Understand these concepts. On the other hand, you say I want to be a computer scientist. I want to be this AI stud, or I want to find out artificial general intelligence, something of that sort. So then you have to get much more deeper into the algorithms, the mathematics of the algorithms. Where do these things come from? Okay, where do these things come from? What is, suddenly somebody tells you binary decision tree, somebody tells you neural network. You have to go further more and say, don't treat them as constructs you should know. Go back deeper and find out what is the origin of these things. If you are going to work along those lines, right? On the other hand, like I said, if you are an applied scientist, you already have a job, those categories, you have to understand how data has to be manipulated. That's your data. because you understand your data more than anybody. Right? That's general. Just because I think there is a lot of confusion, and people are misled. They think some things are cool, and some things are not. That's not important. Okay, this is the important thing. And so once you understand that, that's more than enough. Okay, so let's just go and look at binary relation trees. Okay, it's very simple. I will not even explain anything deeper than what I see in those pictures. But okay, we'll look at this problem slightly before we go any further, right? So again, like I said, no matter what profession you are going into, whether you are applied, you already have a job, and you just want to go be a data analyst in a Swiss bank or something, then you can always remember my number. If you have projects, please give me. But otherwise, if there again, even no matter what you do, it's important to at least try at a superficial level to understand where everything comes from. This is most important, because it helps you know what to apply when. That's all. It doesn't give you anything more than that at any point. Okay? That's useful. In your job, it's useful, right? Okay, so let's look at this problem, right? I'll just show this. I'm sure you've seen this. How many of you have seen this? 1, 2, 3. Yeah, all these computer science fellows would have seen this. Yes. Okay, good. That's okay. Doesn't matter. Okay, just repetition. That's okay. All right. So this is like a toy problem. This is what everybody calls toy problems, right? Something you make up to understand concepts. So this idea here is you have to decide whether you want to play tennis or not. Okay. So once again, you are saying, what's the point? I'm talking about medical imaging and all that. What will you do? It's the same thing. You have to decide. You take a pixel and you decide whether it's tumor or not. Exactly the same problem. Same things apply, and you will see. And these outlook, temperature, humidity, wind are the features. It's very similar to the features I showed you for deciding the heart condition, right? N systole, N volume, N systole, diastole volume, etc. You might as well put them there. So these columns might as well be those N systole volumes, N diastole volumes, I don't know, myocardial volume, so on and so forth. This could be tumor, heart condition. What is this? Either 1 or 2, let's say. One of those. Okay. Yes or no? You have a bad heart or not? Okay. Same. It's going to be the same. Okay. So the outcome is either yes or no, which is 0 or 1. Okay. So all of these are categorical variables, or you can represent them as one hot vectors, right? One hot vectors means if you have for a particular variable or a parameter, let's say outlook, right? Outlook is what are the different types there? Sunny, overcast, rain, 1, 2, 3, sunny, overcast, rain. So let's say if it's sunny, I say 1, 0, 0. If it's overcast, I'll say 0, 1, 0. If it's rain, I'll say 0, 0, 1. Okay. Right? Yes. So the red comes from all the yes, the black from all the no's. Okay. So if it's so let's take D3. If it's overcast, hot, high humidity, winds weak, you say I want to play tennis. Okay. And there are other conditions where you say no. Okay. Now I give you this table. Okay. And I want you to write a program. Okay. Which outputs yes or no, given these 4 variables. What will you use? What will you do? I'm sure you all taught some programming, right? No? Flowchart. It's just some pseudocode, right? Pseudocode. So tell me pseudocode. Not the exact pseudocode. What will you use? What programming construct or pseudocode construct will you use? Yes, exactly. If then else. If this, so nested if then else statements or a series of if then else statements, like several pages long, and you will get the answer. So this binary decision tree is just nothing but a generalized form of an if then else statements. That's all. Okay. It will work for everything. You won't have to worry about specific variable types. It will work. Throw it at it, it will work. Okay. That's all it is. That's the way you understand it. Okay. Right now, that's how you understand. So it's binary decision tree. It's not a general decision tree. Because binary decision tree, because like if then else, you can only split twice. if else, right? If though that's why it's binary, only 2 splits every time you get. Okay, so how will you split? Okay, so it's very easy. Okay, very easy in the sense conceptually, programmatically, a lot of implementation available. If you are somebody who wants to prove yourself, study one algorithm and program it yourself. Okay, so this is a good place to start more than anything. If you want to learn programming, this is a good place. If you want to do ML programs, good place to start. Okay, so what it does is, okay, what does binary tree do? Okay, how do you do this? You take all the features. Okay, this is the root. This is the root. It's kind of upside down. The root is up there. Okay, actually be down. Okay, root's up. That's okay. Upside down tree. The root is up there. So at the root, you have all the features, all the variables. Okay, what you decide is you will choose one of these features. In this case, chosen temperature. Okay, so you decide, okay, if temperature is greater than mild, okay, if it's yes, if it's yes means I split to the right, no means I split to the left. Okay, my right, my left. So you are based on what you see on the screen, it's the same, right? Right and left. Yeah. So then, so we predict where to play tennis or not play tennis. You use the given data, right, or the features in the data. And you split the data into groups based on a given feature. Okay. So you say that if temperature greater than mild, I will always play tennis. So all the data points corresponding to that condition will come to the right node. All the data points that is not supporting that condition will go to the left node. Now then you come to this node and then you say, you look for humidity. And you say if humidity is normal, then I will play. Then all those data points which corresponds to temperature greater than mild and humidity equal to normal will come to the next node, this node. So on and so forth. So now the question is, finally you will come to this end where you don't do any more splits, and these are called the leaves. Depending on which leaf you land, you take a decision. Okay. Now the question is, how do we choose these features? How do we choose the splits? Right. So at every node, this is called the greedy algorithm, because at every node you just make the locally best possible split. It doesn't matter globally, it need not be right. Okay. So if I split, so the way to do that is, okay, let me go back here and show you. Let's say you decide, right, whenever, like you said, how do you choose that threshold? You choose a feature, temperature, right, and you say whenever it's greater than mild, I will play. Greater than or equal to mild, I will play. So you count all the times out of this data set, all the times that it's mild or greater than mild, and that you play tennis, and the answer is yes. Okay, and if you are correct most of the time, let's say how many S's are there? It's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's say 7 out of 9 times, if it's greater than hot, you are playing tennis. That's a good split. That's great. That's locally, it's a great split. So you found that one variable wherein if you threshold on that variable, you get really good answer. That you are correct more than 50% of the time, let's say. That's how you split the data. So the way you split, when I say split, I really mean split, because then the data flows into the next 2 nodes based on the split. So all those which say yes will come to the next right node. All those which say no will come to the left node. The data itself will be split. So on the remaining data, you choose another feature and you split so that you get the best possible. When I say best possible, you want to be right 100% of the time. So you know this answers. So this is your training data. So you know all the features and you know the correct answer corresponding to all these features. So you start at the top, you randomly choose a feature, let's say, and you decide how can I threshold this feature so that I get the best possible answer for playing yes or no. That's all you do. And you do that at every node. If you do that, that's called greedy optimization. So locally you are optimizing. Okay. So that's the, so this is actually a greedy method, surprisingly works very well. Okay. And, and it's also interpretable, because you can always see where you get the best split, right? Because on one variable you will get a very good split wherein you are right mostly, and you know that has the most impact on your decisions. Okay, so let's walk through some of it. Okay. So start with the feature in the data and make a split based on the feature. Like I say, when you say make a split, you split the data set. Okay, so you have 15 points. So you choose a threshold. Let's say my temperature should be greater than hot, greater than or equal to mild. Find all the data sets that are greater than, for data points greater than or equal to mild. Put it in one node down there. Take which are not less than or equal to mild, less than mild, and put it in another node. That's it. That's a split. And how will you say in this case, this is a kind of a real toy data set where the temperature is categorical. So by the way, all these are categorical. Categorical in the sense, it's 1 of 3, 1 of 2, 0, 1. Right? How do I say that? Because temperature is hot, mild and cool. I can always denote them as 0, 1, 2 or like a one hot vector like I described. So, but sometimes you have continuous variables. Okay? So, let's say temperatures, I actually give you numbers. Then you have to find a threshold in the temperature. So, instead of hot, let's say I'll give you a film right there. Let's say hot is 100, I go 95, 75 is also hot, mild is 25, let's say. Cool is 17, 16, 12, mild is 32. Like that I give you numbers. Then what will you do is you will go through a bunch of thresholds. You start with let's say 20, threshold as 20, look at everything less than 20, everything greater than 20. You say everything greater than 20 means yes, less than 20 means no. And then see how correct you are, find your accuracy. Right? How many times are you right? If it's greater than 20, I will play tennis. And then you go look at the data here. Is that what is the percentage of times I am correct if I play greater than 20? You maximize that. So you can keep moving through all possible thresholds till you get very good result. Then you split. Okay, that's how you do the splits. Okay. Now this is not actually the best way to split. I'll tell you why later if I can. So you continue splitting. So then you go to the left node, you have half the data points, let's say, and you split that on another feature. Keep splitting till you get to a point where you shouldn't do this. Ideally, it's called overfitting. You'll get to a point where the leaves, these are the last nodes or the leaves. They have exactly one type of answer. That is either it's 0 or 1. Okay. All the leaves are so-called pure because it will either say yes or no. In the sense, it will have all the data points which contain yes, I will play tennis, or no, which I don't want to play tennis. Okay. So in this case, the way you stop leaf nodes are pure. In the sense, each leaf node will contain only one class. What do I mean by that? If you look at, like I said, you keep splitting the data. At some point, you will hit a node where the node contains only one type, one class. So only all the yes, I will play tennis class, or no, I won't play tennis class. In this case, right? So that's one way of stopping it. That is not a very optimum time to stop because this is called overfitting. We won't go into details. Some of you might already know that's okay. A maximum depth is reached. So not to prevent overfitting, you won't keep doing this, but you will only do it, let's say 3 or 4 levels or 5 levels depending on how many data points you have. Or you have some performance metric. Okay, and if that is achieved, then you will stop. Okay. How to make the split, right? So that what I described is kind of like a very crude way of doing it. You look at classification error. You set the threshold and say everything greater than that threshold, I will play tennis. Everything less than threshold, I won't play tennis. Then you have to look at whether you classified it correctly or not. What is the percentage of times I was right when I do this threshold? Right, you can use that. Okay. I'll only walk through that. Right. So the classification error equation is 1 over, and I have to actually do this myself because I haven't done this in a while. Okay. So you have to forgive me if you do that, right? So, so in the science, let's look at yes. Okay, let's look at the times I say yes, I will play tennis. So the classification error is in this case 1 minus 8 over 12. Okay, so that's the maximum probability. So in this node, you have 12 data points. 8 is yes, 4 is no. Okay, so the maximum probability corresponds to that. So 1 minus 8 over 12 is 0.33. You can do the similar calculation for the left and the right node. For the left node, it's 1.5. Okay, and for the right node, it's this is actually weighted. So 1 point. Did this get done? Did I do the right node? It's 6 over 8, right? 3 by 4, is it 0.75? Yes. 1 minus 6 over 8 is 0.25. That I missed this one. For the right node, it's 0.25. So then you have to look at the change. In this case, what happens if you use this metric, it's called the classification error rate, the change becomes 0 and you stop splitting. Okay, so it's a bad metric to use. There are other metrics like, for instance, entropy. Again, I'm not going to explain this too, because I think best left to your regular classes. I don't want, because they are taught a certain way and I teach it a certain way. Okay, let's not worry about that. So let me, general philosophy I'll tell you. Okay, before classification error rate, I just want to show you that it's a bad idea to do use. But general idea is, see, when we split, we start with a node at the top, right? I'll just show this example. Let's say here, this is your training data, by the way, please remember, you know the answers. 12, let's say 10 yes, 5 no. Okay. What is the idea behind the split? You want to split into 2 child nodes as there. Okay. What is the child? So what is it? What do you want to do specifically? You want it so that everything here belongs to a particular class. Idea, what is the ideal split? Tell me what is the ideal split. What should be in the left node? You can do any class, but it's fine. Ideally, each node should have 1 class. That's the ideal split. So, if I come here, 10 yes should be here, 5 no should be here. This is the ideal split. This is called a pure. So, that makes it pure node. So, I choose a threshold or some criteria wherein I split it. Less than something means to the left, greater than something means to the right. Then I want it split so that you are right. So in the sense 1:1 in the sense everything on one node is yes. So when I come to this node, I know it has to be yes. I want to play tennis, right? But this is not achievable if you are looking at one feature at a time, because you saw that your decision is complex. You are looking at different combinations of these things. So you want to be as pure as possible. So that's the whole point behind it. You want it so that, ideally, okay, it's okay if I am wrong a little bit. So which means, I will strike it out because the eraser isn't working that well. So let me find the eraser. Yeah, okay. So it's okay if I do something like, I do 8s, and in this case, let's say 2 no's here, right? And here I do 2 s's. This is not exactly the best, and 3 no's. I split so that, a lot of the s's are on the left. That's one good split because it's mostly pure. It's mostly pure in the sense it's mostly yes. Then you can think of further splits. And you can stop here actually. You can stop here. Okay? You don't have to go till, what I'm trying to tell you is you don't have to go till you make pure nodes. You can stop when overwhelmingly one class dominates a node. You call that a leaf. Okay? So that's the point. So, so what people typically do is they will grow the tree. They'll keep splitting till they get pure leaf nodes, like I showed first time, where all the points that end up in that leaf node belong to one class. People will grow the tree till that point. Of course, when I say people will grow the tree, is figuratively speaking, you write the code so that you exit the code when all your leaf nodes become one class, right? So when that happens, then you can go back and so-called pruning happens. In the sense you will try to get rid of it, some of the nodes, and stop early. The reason behind that is what happens when you go to a point wherein all the leaf nodes are pure, it's called overfitting. So typically your data is noisy. Okay, you might have some wrong features there, wrong labels here and there. When you fit your data perfectly, then on test data it won't work very well. Okay, this is a problem. It's called overfitting. So you won't overfit typically. You won't go till you get pure leaf nodes. You will stop in bit much earlier than that. Okay. The condition, the only thing you have to understand is the condition that you use for splitting. Okay. So and what, in a sense, how do you figure out where to split? So you have a feature, you have to know where to split that feature and what is that condition. That's the important part behind binary decision. I showed you one condition wherein you look at the classification error. So if I take a threshold of mild and I split the data set into two, yes and no, what is my classification error? Am I getting it right or wrong? So that's the idea. Okay. So in the sense that if I go to my left, what percentage of data set did I classify correctly? I say I will play tennis if it's greater than mild, then I get a bunch of data points here and I look at, and I have the ground truth, right? No S. Then you see whether I was, what percentage of time I was right. And you want to maximize that. That's the criteria you want to maximize. Okay. So then if you are able to maximize that, that's the, you can keep changing your threshold if you maximize. And most decision trees are grown that way. There is no clever algorithm, it's brute force. If it's a continuous variable like temperature, you have to keep varying the temperature till you get very good classification, the best possible, because you are only thresholding on one feature. When you are, when you grow your tree all the way to the leaf nodes, where each leaf node is exactly one class. So when the new data comes in, there might be some errors might happen. That's the only thing. There are ways to get over this, but anyway, right there. So is that clear? The explanation. If not, this is the simplest algorithm out there. Okay, so it shows this. Yes.
So you said that this type of classification is not good.
Which one type of classification? Error based on classification error. Is that what you're saying? So okay, just to clarify. Okay, so what I'm saying is, all right, let's just go back. See, so we start off with, I just draw here again, just to, sorry about this, I am so used to that other one, doesn't matter. So this is your root node, okay. This has all the data points, I think 14 data points here, right? All the data points are here, okay. Now you want to split it into left and right. This is the first step, okay. The first step, you want to split it into two data sets where you are claiming that this one, yes, I will play, this one, no, I won't play, okay. For every data point here, you have the, you know the label, yes or no, you know that, okay. Now, let's say you choose temperature as the first split. You can only choose one feature at a time, typically. So you will typically one feature at a time. So you can choose two also, typically to choose only one at a time. Let's say you choose temperature. How do you determine the threshold? That's the question we are trying to answer, right? How do you determine greater than or equal to mild, greater than or equal to cool, greater than cool, or anything less than hot for all temperatures, to say you will play, yes, I will play, okay. So let's say if you choose greater than or equal to mild, which means whenever the temperature is mild and whenever the temperature is hot, in that particular data point, you will say label is yes, okay. So all of them will come to the left node, all those data points will come to the left node. So once you have chosen that way, what you do is, you look at what you have labeled as yes, I will play, and what the correct label is, and you compare, okay. How many of them did you get right, okay. So in this case, let's actually do it, okay. Okay, let's say you decide you will play whenever the label is greater than or equal to mild, alright. So let's just count how many are there. So that's like 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times you say that you will play. But of these labels, how many of them are actually correct? Right? Because you will play, you say 9 is yes, but if you look twice when it's hot, I will say no. Okay, so that's the misclassification error I am talking about. Out of these 9, how many actually did you get correct? That rate is, so then you can also write down out of these 9, how many of them are yes, how many of them are correct or no. That gives you an idea. So you want to maximize that or minimize the misclassification. In the sense, out of these 9, if 8 times you are correct, great. That's a good split. So you have to keep varying your threshold for that particular feature till you get the maximum possible value of your classification error, or the minimum possible value of your classification error, or correctness of your classification is maximized. Okay. So this is done brute force. There's no clever way of doing this. So if you have a temperature range, for instance, somebody gives you values of temperature between 1 to 100 in Fahrenheit or 20 to 100 in Fahrenheit, you have to step through. That's another trick. What is your stepping? 1 degree at a time, 5 degree at a time. As you step through threshold and see every time how many you are getting correct. You maximize that correctness, you are done. Then you split the data, go to the next node, choose another feature, find another threshold, so on and so forth. That's how you grow. Okay, that's it. The thing is, how do you, this classification error I said apparently is not a good metric. That's what I meant. So looking at it, yeah. So that's not a good metric, because sometimes even after a poor classification you will get 0. So what people do is they look at information gain, so called. So before and after split, what was your, so that's what happened in that example I gave. So classification error before and after classification, when you split into 2 and you look at the difference, classification error change is not much. You haven't achieved much. That's what it shows. So it's a bad metric to go, but it will work. You land up in this weird situation sometimes. But other than that, it's fine. But there are other metrics like I said, where I mentioned it. Damn it. Entropy, and there is one information grain. Okay. So let's not worry about that now. I don't want to get into those details. Okay. Because I thought I will talk about it, but I think it's not worth it right now. You will. Somebody will teach you that in your machine learning course. Don't worry about it. But this gives you an idea about. Okay. So now you know to do this. This is what people do in medical imaging also. So now you take this algorithm and you see how you want to apply it to, let's say, medical imaging analysis. There are 2 ways to apply. Okay. So one I show you here. The one I show you here. Hold on. Here. So instead of sunny, temperature, wind, etc., you have volume at ED, volume at ES, ejection. These are all numbers. And these are again all numbers. So instead of 4 categorical variables, you have about, I think, 12 or 14 numbers here. So that's your feature. So at every node, you will choose one of these features, figure out a threshold that will split optimally. You keep going till you get the leaf node. The leaf node where you will put here, of course, you can, in this case, I'm simplifying it. Here it's not 2 categories, there are 5 categories. The way you would do 2 categories is you can do one versus the rest. Say normal versus abnormal, okay, and take one of the diseases, let's say myocardial infarction versus the rest. You can do stuff like that, okay, one against the rest you can do. You can have 5 different, so you'll have 5 different algorithms, okay, for 5 different conditions. That's one way of doing it. And you can also do multi-class category, but not to confuse you, I'm just doing it very simply. So, the same algorithm, so this is one of the things that people like about even deep learning, even machine learning. It's the same algorithm, you don't have to code differently. All you have to do is figure out these features properly. Okay, this is after the fact. Let's say, how do you want, let's say you want to do, this is not a good place to do this. Let's just go here. I'm just doing this in a very hand waving way, but it's good enough. Did I have this here? Okay, here. Alright, this is a good picture to work with. Okay. So now, let's say that was for disease classification, right? I just said as a disease classification. Now let's say you want to actually do segmentation. So let's say I want to label every pixel. Now you see the scale of the problem has grown. How has it grown? So when I want to do disease classification, I have only to work with what? Patients. So the number of data points is equal to the number of scans I have. Right? That clear to everyone? So for every patient there is a scan. I do the segmentation of the scan. And I extract 12 features from the scan. So every patient has 12 features. And my number of data points is equal to the number of scans or number of patient scans I have. That's all. Okay. If you come here, I want to categorize every pixel as belonging to, let's say, tumor or no tumor. 2-class problem. Same as yes or no you saw for playing tennis. I want to say tumor or no tumor. Essentially, I want to do this segmentation. I want this. The entire tumor is highlighted there, okay. I want that yellow thing, whole thing. So then if I pick a pixel from here, I would like for the binary decision tree to say yes. Pick a pixel from here, I want the binary decision to say no. Okay, now what is the scale of this problem? See, I'll tell you the problem. A typical MR volume consists of 256 cross 256 cross 256. This is the array size. Okay, so what is this number? Fairly large number, right? Just 10 raised to 1000, right? So almost how many pixels are there? You can imagine these are the number of data points. This many data points. Okay, this because I want to categorize every pixel or voxel in my picture as belonging to tumor or not tumor. Of course, you can solve this problem slightly easily by drawing slightly smaller box. Approximately, you know where the tumor is. You can ask someone to draw a big box around it, cut out most of the pixels. Even then, a tumor itself can be 100 by 100 by 100. You can do, let's say you cut it down to 100 plus 100 plus 100. So that's how many? 10 raised to 6. Okay. So 10 raised to 6. So for every image, I need to classify 10 raised to 6 pixels at least. Almost a million pixels. So I have a million data points. So every pixel is a data point. Unlike there, the previous thing I showed you, every patient is a data point. So I might have a few hundred, few thousand patients. Now I have 10 raised to 6 data points. So for each data point, I have to extract a feature. Now there are no, I haven't shown you how to extract features for this. For the patient disease classification, I showed you, end systole, end diastole volume, myocardial volume, etc. Here, you have to be clever about what kind of. So for every pixel, let me give you an idea of what can you do. Let's say this is a pixel. I put a small box there, small point there. Okay, that's my pixel. Okay, I want to classify this pixel as 0 or 1. In the sense, let's say I want this to know whether it belongs to a tumor or does not belong to a tumor. So now for this data point, I need to extract features. Lots of features in it. So easy way, you put a box around it. Look at the mean standard deviation inside that box. Okay. Other clever trick is, I put a box. See, this is called the, I shouldn't venture into anatomy. See, the brain is symmetric. Okay. Left and right half in the picture, the images. So if I draw this line, just like a bad line, okay, but I find the corresponding reflection of this point on this side, okay, and I want this to be similar. It has to be similar. It's alike. Both sides are alike, especially in the image it is. So then I can do a correlation of, let's say I find the corresponding point on the mirror image, on the other side of the brain, put another box there, do a correlation. It should be highly correlated. Okay, if the tumor is there, it won't be correlated. Okay, I can do many other things. There are thousands. There are texture features. So for every pixel, I can get an array of numbers. Each one of them. So I will call them for pixel. I'll call each pixel xi. Each pixel xi I can run from 1 to n features. Each of them numerically you have to cleverly do this. Okay. And again, this is for one patient. Okay. So when you train, you will have, let's say, 100 patients. For 100 patients, I have this data. So for 100 patients, for every patient, I'll have to choose subsets of pixels belonging to the tumor, not belonging to the tumor, make a feature vector for each one of them. So I can get millions of data points. Train that with a binary decision tree. Okay. So that is the difficulty of the process. Okay. Especially the feature extraction. Forget the size of the problem. Okay. So you see the asymmetry here, right? You have millions of data points. So when I say, maybe I'm not bringing that point across properly. Where can I? Don't worry about this. I just need a place to do this, right? So this is the data points, data point index. So when we did the first cardiac thing, I had what, 1, 2, 3, 4. Let's say I had 100 patients. So I had 100 data points for 100 patients. Right? Each patient had, let's say, 1 to 12 features. That was the problem, right? If you remember, I can go back to that slide, a list of numbers. You saw that even the importance of each feature, but 12 or 20, maybe 20 numbers. So hundreds of patients, tens of features, right? When you are trying to do image segmentation, the data point is a pixel. So I will get 10 raised to 6 at least per patient. So if I have 100 patients times 100, so that will become 10 raised to 8 data points at least. I can have billions of data points, pretty much. If you take a few thousand data points, even if you take 1000 data points per patient, I have 100 patients, I get 10 raised to 5 data points. But if you look at the features, how many features can you make? 10, 100, how many features can you extract manually? Just by looking at the picture, thinking of something clever, which makes sense in a diagnostic sense. Not much. Tens, maybe 20, you can figure 100 features. Right? So there's a dimensionality mismatch here. This is an issue. Okay, you can have, so because the patients are varied, every patient will look slightly different. The grayscale values might be within a range. Okay, but you have this problem where you have hundreds and hundreds of patients. Each of them have thousands or even tens of thousands of pixels. Each pixel is a data point. So that's how you train for image segmentation. You have to understand how to extract those features. So that's the size of the problem suddenly changes when you try to hit things like image segmentation. Okay, so this is the fundamental bottleneck, right? But people have done it and they've gotten decent results. Okay, you can go and look at random forests and binary decision trees for image segmentation, medical image segmentation, or brain tumor segmentation. People have done it. That was what is on the other PDF, but it's okay. I don't want to confuse you too much. It's okay. But the general idea is, can you, how do you scale these problems? It's very good on a certain size of data, but binary decision trees have been used for, and there is variation of, not I wouldn't say variation. Another algorithm that exploits binary decision tree is called random forest. The way random forest works is, you have all done statistics, right? You must be right. Okay, good. So if you go to, I will just explain random forest as it is. I don't want to go through this. See, we looked at this binary decision tree, right? I didn't draw a full tree, which is kind of bad. Okay, look, that's there. Okay. So now you start off at this is the root. You start off with some feature x I. Okay. So you start off with a certain feature. That's how we start splitting. Okay. What you want to do is, you can create more trees like this. So you can start off another tree. Let's say you start off with feature x1. You can do another tree we start off with feature x2. So on and so forth. You can, and in fact, when you come to the splits, right, you can leave out features. You can choose features randomly. You don't have to use all the features. You can only use some of the features. So when you do that, you can create a bunch of trees. Let's say hundreds of them people use sometimes, which are uncorrelated. Okay, you can correlate. What do you mean when you correlate it? See, because if you don't make this change, randomly choose a different, consciously choose a different one, you will end up with the same kind of splits. You can have the same kind of, that doesn't help. Average the same thing again and again. So you have this variance that you create, and if you average these results, you get very good accuracy. So that's the random forest. I'm annoyed by this writing. I have to be very careful. I end up pressing some weird. So the random forest, that's the principle. You create this. You take it's a binary tree only, but you create a bunch of them, and you average over the results. It's called ensembling, and you get a better result. Okay. So I won't go into detail again. Just to give you an idea of how these are exploited, and this can be used for image segmentation. Image segmentation problem is much larger. One way to solve the image segmentation problem is knowing the size, that you sample. So you don't have to take millions of pixels. You can exploit the fact that pixels are redundant, right? So I'll show you again. Sorry to go back and forth, but I just want to make that point. See, if you look at this area, right, they are similar. Okay, so you don't have to choose like, you can choose like 10 pixels from that area. You don't have to choose every pixel there. Similarly, certain areas are very similar. These are all similar looking or similar statistics. So you just choose a few pixels. So you can sample your data. From every patient, you sample a few thousand pixels. That's your data point. Then you can make a 10,000 data points, few hundred features. You're ready to do segmentation. Okay, but in all this, what are you missing? There's one feature I haven't talked about, which you should all think about. This is an image, right? So what is it that I'm missing out here? What? Size is one thing, yes, but what exactly other things? Huh? No. Huh? Volume is there. We can connect. We can count pixels, calculate volume. See, the picture has structure, right? So if you have a picture of a face, the position of the eyes, nose, hair, chin, it has meaning. Yeah, location of the different components of the tree, that you are missing out because you are looking at it piecemeal. You are looking at individual pixels. But that's the best you can do here. But you can still do, for instance, you can do a shape feature. You can look at the neighborhood of this and try to pick, let's say you do edge detection and see how strong an edge is. So you can do shape like, and you can use derivatives to calculate shape like features, right? You can see that. So that, if you incorporate, your predictions might get slightly better because you have to take into account neighborhoods. It makes sense that the brain looks a certain way, right? And you have to incorporate that looks a certain, that appearance, it's called appearance. The appearance of the brain you are not using anywhere here. Whatever I have described to you, it's all statistics. That's what you are using. I have only told you statistics. So how do you incorporate quote unquote shape, appearance? You can do that too, but you can do that by hand. It's hard. That's all. You can do it. So the reason I told you about all this is what leads to the next step. Why people like deep learning? Why people love this? You must have all. How many of you have not heard of deep learning? So called. Not heard of it. Okay. I didn't want to see a bunch of hands. Good. Everybody's heard of deep learning. The reason why people are excited about this is you don't have to do this. So all this stuff is extracted automatically. And that's what we have exploited in that heart problem I showed you. They use deep learning to get the segmentation out and extract some of the features from there and use that for diagnosis. Okay. So that instead of sitting down and figuring out this, which is again what you see, again, in the context of medical imaging, given the sheer size of the problem, millions of pixels, hundreds and thousands of patients, in fact, many cases there are millions of patients, we just don't have access to the data in one shot. This is kind of cumbersome, it's impossible to do. But in many cases, let's say where specialized knowledge is required, it's okay to use that knowledge. So somehow, again, this is all in the very what I'm telling you is not some philosophy, it's practical advice. You have a job, somebody is giving you a job, let's say you're working for Goldman Sachs and they want to figure out, stock prices. Of course, I'm not advising you cheat, easier ways to do insider trading, but in the not doing that, if you want, you have to use business knowledge, right? Domain knowledge should be incorporated in addition to that. Yes. Yes, it does. That's okay. We have a lot of, one of the reasons why these deep neural networks now have taken off is because computations have caught up. So all these algorithms run in very fast time. CPUs are also fast. The only inefficiency here is the feature extraction, training, etc. Okay. Yes, you can run these algorithms there. So it's okay. So of course you have to pay for it, but as long as somebody is paying for it, yes. I really don't know, but the one way is, see, the way people try to do that is they have a validation set. So when you train, so I haven't talked about this again, I don't want to get ahead of the game because you will be introduced to these things in the course systematically. So when you train, right, so let's say, we'll go back to our little time, what time then when I thought I had time, it's running out, right? Okay, so let me just quickly do this. Answer is a very good question. He is just asking me, see, I said this greedy algorithm, right, because you're optimizing locally. At every step, what is the best possible split? So that doesn't mean, so the ideal way to do this is to grow the entire tree. And you grow thousands of trees and see which one is good. But you want, it's computationally hard. So the way you would do that is, you won't take all these 14 data points. What you will do is, you will keep aside, let's say, 5 of them. Okay. And you will not use it for training, for building the tree. Okay. So, and once that 5, that is basically 20% of the data or 10% of the data you keep aside. And after you are finished this business of actually figuring out the correct tree, you will test it on that validation set and see the performance. If it is below par, it's not as good as your training and worse than training. Let's say with training you get 90% accuracy, this gives you 60% on the validation set. You know you have overfit. That's when you redo it. But see, it's a danger there, because you will tend to overfit on the validation set. Okay, so you have to be careful. So you have to have, best to have multiple splits of the data. So they'll have, like, you have 3 or 4 splits of the data, you use only one split to fit. And in fact, there's another way, you can keep aside a different 10% every time. So let's say I have 14, I can choose 4 different data points 4 times. Leave those out and train with the remaining. It's called 5-fold or n-fold validation. So you can do that also. So these are ways to ensure that, like you were talking about, you don't end up with some suboptimal kind of training. Okay. All right. Any other questions? I'm going to stop. I'm done. Any questions? Yeah, go ahead.